Lesson 33, electromagnetism. Now, there's a lot of stuff you can do with electromagnetism, and if you're bored someday and you have some wire, a battery, some nails, some other stuff, go on and find some experiments. But the one we're doing today is Orsted's experiment. And so what we have is we have a coil of wire that we can run electricity through this battery. I find that rubber bands work pretty well to keep it clipped on there, and a couple of alligator clips if you have them. And then we have a magnet. And for today's magnet, we're using this very tiny little compass, which
you said today's magnet, but
it is a magnet. So a magnet, a compass is a magnet. So one end of it is south and one end of it is north. And so a very small magnet balanced will always point towards magnetic earth towards magnetic
north.
Magnetic north, which isn't the same as the North Pole, but it's another subject. Okay, so it points towards north. See, north. And if you don't know how to use a magnet, just real quick, it always points towards north, and then you have to orient north to the little bar. It's not that it's supposed to point towards north.
Toward the end.
Yeah. Okay. So you'll probably cut that out. Anyway, so we have a very small magnet inside an electro field, so a loop of electricity. So as soon as Levi hooks that up, there's now electrons traveling from one end through this loop back to the other end, from positive to negative. Okay, so you can see that we're pointing towards north. So plug it in, Levi. But now as I move close to this, it really messes with my magnet. So I'm creating an electromagnetic field, which is more powerful than the Earth's pull. And so it causes it to move all over the place. And if I can actually get it in there, it will just lock that up and make it nice and rigid. So now,
it's locking what up? The magnet?
yeah, so now as we turn this, it stays oriented to that thing. It no longer points to the loop.
It's loop, oriented to the magnetic loop instead of the magnetic north. You keep moving it around. Hang on.
That's not ideal.
I know. It's really hard to see.
Okay, so to demonstrate this better, we still got the loop, and we put the magnet on this little spoon here so you can see it a little better. So see, if I move it outside that electromagnetic field, it's pointing more towards north.
Now the compass itself isn't oriented towards N, but the red piece is pointing north always. The red dot. Okay. Okay.
Okay, so now if we hook up our electromagnetic field and we go to put our magnet in there, you can see now it orients itself perpendicular to the loop.
So north is a different direction now.
No, north is the same direction. It's not, the magnet isn't pointing towards north anymore. There we go. See, so I can
move it slower.
This.
Now it's not turning at all.
Well, it's oriented to the magnetic field, not to magnetic north. So as I move the magnetic field, the electromagnetic field, it stays oriented to the same direction as the loop.
I see.
Move it outside.
Then it moves back to magnetic north.
No, moves. It's still being influenced by the electromagnetic field, but it turns in a different direction. See.
Oh.
So if you did this, you could map out what the electromagnetic field looks like, and you'd see loops of electromagnetivity going around.
Oh, outside of the circular.
Mm-hmm.
So how far outside of this loop do you have to go to get back to your true north? Your true magnetic north.
So I'm back to north, and then as I come into the field, it becomes more and more influenced by the. So now it's not being influenced, it's pointing towards north. You see it turns around.
I'm just curious. Would a compass be rearranged like this, going underneath a bunch of power lines?
No, because they're traveling in the same direction. If there's an electromagnetic field or there's loops, then there would be, but just electricity traveling in a straight line doesn't do it.
Oh, okay.
Okay, so Faraday's experiment is much like Orsted's experiment, except for backwards. So instead of this time putting electricity through this loop with a battery, we're going to put a magnet through the loop, and we're going to generate electricity. Okay, so this is our voltmeter. Right now it's set up to read amps, so it's actually reading current, and it's a very, very small amount of current, as small as we can go. Okay, so I'm going to take this magnet, and I just made it twice as long by putting the two magnets together, and then I'm going to move it through this field, and you'll see that we're going to generate a current. Not a really big current. And you'll also see that if I stop in the middle, there is no current. So the magnet actually has to be moving through the field. So the faster I go, the more current I generate. So it's hard to see because it has to wait to like generate it, but if I can move pretty fast coming out.
You mean it takes a couple seconds for it to show up on the screen?
Right.
You got 12.12 on the last one.
If I go too fast, it'll generate the electricity, but the voltmeter won't pick it up. So if I just drop it, it doesn't.
Yeah.
It's too fast. But if I had a really long magnet and I dropped it through there, I'd see a much more interesting result.
Yeah. So is the electrons are just kind of hitting each other fast?
I don't know how to answer that, Jody.
I just have so many questions right now.
No.
Okay, fine.
This is organizing the electrons and getting them all to flow in the same direction.
Okay.
So the magnetic field orients. It doesn't cause them to smash against each other.
Okay.
Okay?
Yep. You're on.
Okay, so Jody was asking if all the electrons were running into each other, and I was saying, well, no, not really, but they kind of organize themselves. So that made me think that we could actually generate a diagram of an electromagnetic field. So what we have on the ground here is just a magnet. I'm going to cover it with a piece of paper. And then we have a whole bunch of iron filings here with some sawdust mixed in. Sawdust isn't useful, but iron filings are. So now we're just going to try to spread this out over the paper, and all those little iron filings will orient themselves into the magnetic field of the paper. Please don't rub the paper. Thank you. Okay, so you can now see you have the north and south pole, and then it makes these kind of shapes around. So you see there's this like really tight thing here, and then it spreads out from there, and then it makes these loops.